All right, I guess everyone's silent, so I'll go ahead and get started with the intro. So thanks so much for coming. It's my pleasure to introduce Scott Kuindersma as our speaker today. So Scott is the Senior Director of Robotics Research at Boston Dynamics, where he leads the Atlas humanoid robotics team and also other mobile manipulation efforts across Boston Dynamics. So as it turns out, I guess Atlas is the latest in a long line of humanoid robots that Scott has worked with over his career. So he received his PhD at the University of Massachusetts, where he worked with Rob Ruppin and Andy Bartow on really efficient learning of dynamic behaviors on the U-Boss humanoid robot. And then he also spent some time during his PhD at NASA, at the Johnson Space Center, where he worked on their Robonaut effort on manipulation and control. After that, Scott worked as a postdoc at MIT with Russ Cedric, where I had the pleasure of being Scott's lab mate for about 3 years or so, where he led the controls efforts on the MIT DARPA Robotics Challenge. Working with, I guess, a previous incarnation of the Atlas humanoid robot. After MIT, Scott joined the faculty at Harvard in the computer science department, where he led the Harvard Agile Robotics Lab. And I remember maybe, I guess, a couple of years after Scott joined, I ran into him at a conference, and he made this observation, which I found interesting at the time and has kind of stuck around with me, and I remember thinking about periodically, which is some version of nonlinear model predictive control and optimization-based control is kind of all you need. And yeah, if you can really scale these methods up, we can get really amazing results for locomotion and potentially even manipulation. And over the past 4 years or so, Scott has been demonstrating exactly that. As you've probably seen, video after video, demo after demo, you can do some truly amazing things with these techniques. So Scott, it's wonderful to have you here. Thanks so much for taking the time.
Thank you, Ani. I'm going to have you write my bio.
That was incredible. Wow. Hi, everyone. Happy to be here today. So today I'm going to tell you a bit about the work that we've been doing mostly on Atlas over the past few years. Tell you a lot of the motivations that's behind the research that we're doing and where we kind of see this research leading to its next steps. But to start, I want to spend just a couple minutes giving you a broader overview of everything that's going on at the company, where we're coming from, what our goals are. So Boston Dynamics is a company that's been around for over 30 years, and throughout that time has sort of gone through different phases, starting out as a very small-scale R&D company that was primarily funded by government contracts, through a couple acquisitions, the most recent of which was from Hyundai Motor Group. But throughout this time, we've really kind of maintained a pretty consistent vision for what's possible with robotics. And we believe that creating robot systems is a real opportunity to improve the lives of people all over the world. And the way that we think that'll work is that you can kind of use robots to break down the remaining technological barriers that preclude people from choosing which physical labor they want to perform. And so that's what we're all about. And it's, of course, a very long-term mission. And as part of that mission, we're exploring different types of robot platforms and different types of applications in order to sort of incrementally build ourselves towards this long-term goal. So the robots that we have at Boston Dynamics currently, you've probably seen at least a couple of these before. First is Spot, and this is coming out of a long legacy of quadrupedal robot development at Boston Dynamics. This is our first robot product. You know, the way that this worked is we decided we had a really cool thing and decided we wanted to share it with the world. Didn't exactly know all of the ways that people would maybe find value in a system like this, and so Spot quickly adopted a very large customer base in a variety of industries, from entertainment to research and development to industrial settings and so on. Likewise, subsequently we built Stretch, which is a more purpose-built machine that is designed for warehouse automation. So this is, notice it doesn't have any legs, right? So it's an omnidirectional wheeled base and a very strong and capable arm, and it's designed to move parcels around warehouses. And then, of course, we have Atlas, which is primarily our R&D platform that sort of captures our vision for what we think future robots might be capable of doing. So, like I said, Spot's being used all over the world for different things. We've sold over 1,000 of these robots at this point, and they are on every continent. Maybe not Antarctica, but all the other ones. And there's a lot of different ways people are using it. One of the use cases that's really taken off and has shown a compelling value proposition is industrial inspection. So there's a lot of need for just having robots that can capably move around different types of environments, over stairs, over obstacles, and collect data about those environments, whether that's building digital twins, whether that's reading sensors on legacy infrastructure, taking thermal measurements, detecting sound anomalies, and so on. This is really a great use case for Spot, right? And so you can take Spot, you can outfit it with a variety of different sensor payloads, and you can actually derive value from the robot in this way. Likewise, Stretch has started to make its way out into the real world as well with early customers, including DHL, Maersk, H&M, Gap, and a couple others. And primarily the use case for Stretch is container and truck unloading, right? So this is a very physically demanding task that's currently being done by humans, thousands of humans all over the world. And so Stretch is a solution that can go into the back of trucks, be able to detect packages, figure out how to sequence removal of those packages, work with different types of existing infrastructure like accordion conveyor belts or fixed conveyor belt systems. And the sort of interesting Boston Dynamics twist on this thing is, of course, that the robot has to move fast and it has to be super reliable, right? In order for this thing to have a real ROI case, it has to be the case that the robot need not be babysit by a single person the entire time, right? If you have to have a person who's watching every single Stretch robot do its work and make sure it doesn't screw up, then you haven't really gained anything there. So in current customer sites, the robot's able to move around 500 packages per hour. More recent versions of the code base get that up to around 800 packages per hour, and there's still a lot of room to go there. And it's doing that with around a 0.1 to 0.4% failure rate. And the reason it's doing that is not because it never drops anything or never causes a box avalanche like a person sometimes does. It's because it's able to identify when those situations happen and recover from them without any human intervention, which is a big focus of the research that has been happening on Stretch over the past year or so. So as I said, this is kind of what's going on in other parts of the building, but today I'll mostly focus on the work that we're doing on Atlas. And Atlas is primarily an R&D platform. So we think about Atlas as kind of a technology incubator for the company. We use it to explore new ideas in hardware and software, whether that's actuation technology, new battery technology, communications, compute, sensing, or in the software side, new types of control algorithms, machine learning technologies, software libraries that are generally useful. And we take these components and we graduate them over time into our current and future products. Atlas, I would say, also captures no small part of our brand identity, and it captures a lot of the vision that drives most of the people who work at Boston Dynamics. And so through our kind of viral YouTube videos and things like that, we use it as a kind of tool to demonstrate what we're able to do from an engineering perspective, but also show people glimpses of what we think robots like this might be able to perform like in the future. So Atlas is a robot. This version of Atlas has been around for several years now. This is just a quick overview of what goes on from a hardware perspective. It's hydraulically actuated. It stands about 1.5 meters tall, so it's not super tall. It's only about this tall. And if I were to say one thing about the robot that makes it special, it's that it has a very high strength-to-weight ratio. And that's achieved by a combination of technologies ranging from a nice compact and capable hydraulic power unit that lives in the middle of the torso, custom lithium-ion battery pack technology that's able to deliver huge bursts of power in order to do explosive motions, custom hydraulic servo valve technology, lightweight 3D printed structures that allow us to reduce distal mass and therefore be able to move limbs around very quickly. All of these things combine to create what is a very capable robot. And so that leads to lots of ideas, of course, about what we might be able to get this robot to do. And so a core underlying theme of all of the research we've done on Atlas for the past 3 years has been this underlying goal of making exciting, athletic, expressive behavior easier to create. We have all of these ideas of what we think, and maybe in some cases know, the robot should be capable of doing, and we'd like to reduce as much as possible the barriers to creating and realizing those behaviors on the robot. So what does this mean? Well, of course, we have a very talented team of engineers who could think about any particular problem, like make the robot do a backflip and say, okay, well, What assumptions can I make about backflips? How can I simplify the model for this problem? How can I write a bespoke controller to make this robot do a backflip? There's any number of people at Boston Dynamics who are very capable of doing that. But doing that produces a component thing that's not super reusable, that's very specific, and that whole activity maybe doesn't bootstrap later behavior development. So we wanted to find a way to build an ecosystem of control, interfaces, and offline design processes that allowed us to more quickly, over time, create new types of behaviors. So if I were to draw this as a kind of cartoon of a design space, it might look something like this. We're imagining that when you want to program a robot, there's sort of an offline design phase of some kind. And then there's some online execution phase. And the goal, I think, is to try to make this part as generic and reusable as possible and as flexible as possible so that I don't have to, at design time here, know exactly what are all the different interfaces I might want to use over time to specify behaviors for my robot. For one thing, when we started this work, we didn't really have most of these. And it might also be the case that depending on what you want the robot to do, the interface for designing that behavior could be quite different. If I want the robot to dance versus manipulate objects, I might not want to use exactly the same interface for both of those things. Likewise, there's many different intermediate representations you think you could use to describe behavior, right? There's some obvious ones like trajectories, which is where we started. Other obvious ones might be grasp locations or desired navigation goals, or maybe other pre-computed objects like policies or value functions, right? And depending on what choices you make here, places constraints on how good the stuff over here has to be, how much time it takes to create these things, and how much iteration there is between this offline design phase and getting this behavior to work on the robot. And so the last couple of years have been about us kind of exploring this space in various ways. And as Ani mentioned, one of the choices we made early on was to say, we think model predictive control is a good idea here. That there could be a lot of flexibility in how you set these problems up and what they would be able to figure out for you on the fly, that this job could over time become easier and easier. And so that's really been the basis of a lot of the work that we've done. So I'm going to talk about a few different flavors of MPC that we've played with over the last few years, but I wanted to start with just some general statements so that we're all on the same page. So model predictive control is, of course, a technique for doing control that is optimizing states and inputs over some time horizon to the future and trying to decide what to do right now, not only to improve the state right now or the very next time step, but also to improve how my state will evolve over some time horizon, say a second or two into the future. Very quickly, when you start talking about robots like Atlas, you're in the space of nonlinear model predictive control because any reasonable representation of the dynamics or the relevant constraints for a robot like Atlas tend to be nonlinear functions. And so you have to figure out a strategy for solving that problem. Our approach to doing that is just to linearize it and solve a QP, right? And in particular, we're not ever trying to solve this problem to convergence, right? We're not doing SQP as part of our control strategy. We just, at every control tick, linearize it once and then solve a QP. And we don't even solve the QP either. We just like kind of head in the right direction and then time it out. Why does this work? Why would you want to do that? Well, when you're building a control system, oftentimes the feedback rate is quite important. And you also get this sort of convergence through time property because MPC problems from one time step to another tend to be pretty similar. So over multiple time steps, even though you're not doing multiple SQP iterations, you can tend to converge to a pretty good solution. Other things you might want to do, and almost certainly will have to do if you want to succeed, are to exploit the problem structure that shows up in these. This is a kind of hilarious cartoon of that problem structure. There's been hundreds of papers that people have written about the specific structure that shows up in trajectory optimization and sequential decision tasks. But basically, you want to think carefully about how you write these problems down so that you can do things like minimize the number of non-zeros that show up in your problem matrices and so on. And finally, you probably don't want to just treat solvers as a black box. Okay? Things are always getting better. There's always more exciting solvers coming out. Some of the off-the-shelf solvers you can download or have access to right now are quite good. But you can always almost certainly do better, not only by paying attention to the available parameters of those solvers, but by getting into the source code, changing things like linear algebra subroutines and so on. These things can actually make a difference and can produce pretty noticeable performance improvements on the robot. So in terms of the specific types of MPC we started to explore, we started with this idea of looking at centroidal dynamics. And so this is an idea that was, prior to us starting this work, already out in the literature. So the first I was aware of it was the work that Hung-Kai Dai did. But there's many, many papers of different variations of this type of optimization that have been published. And our approach was to kind of cascade these two optimizations together. So the first optimization here is really just thinking about the robot's center of mass, external wrenches being applied to the robot, how that affects changes in momentum, the robot's angular excursion, right? So this is a very simplified, almost sort of single rigid body approximation of the robot. The output of this would be things like center of mass, momentum, forces. These would get input to a subsequent kinematic optimization, whose job was it to make sure that the configuration trajectory of the robot was consistent with those momentum trajectories and, with the degrees of freedom that are left, stayed close to some reference trajectory. Okay? So why would you decompose the problem this way? Well, it's primarily a computational argument, right? By separating these into two separate problems, each one of them is independently a lot easier to solve, a lot faster to solve, and so we derive that benefit. The problem, of course, is the kinematics don't show up here, and sometimes that matters, right? If I want to know whether my robot can actually reach the ground, right, that's a sort of kinematic reasoning argument, and that's not really well represented here. And so by separating these two things, you're giving something up. You're giving away a certain amount of flexibility. And what that meant pragmatically is that the inputs to this system had to be relatively good, right? And so if I'm inputting a trajectory, the trajectory need not be perfect, but it kind of has to look like the thing you want, right? It has to be pretty close. But nevertheless, by using this kind of decomposition, you can do a bunch of stuff. So a lot of the work that we did, or all of the work that we did in parkour and dance was under this framework. And so these are the kind of things that you can do. Sorry, this is all weirdly colored. I'm not sure why that is. So these are trajectories that were optimized offline using the same type of decomposition that we're using for the model predictive controller online, but we're solving a much bigger problem here where we have many more knot points. And then we also have many task-specific costs and constraints that tell it what a good backflip or a good front flip should look like. So there's a lot of task-specific design happening here, and that allows the MPC to be completely generic. And in fact, any video I show you that has jumping, flipping, running, dancing, it's literally the same exact MPC controller with the exact same cost function, everything. Nothing is changing. The only thing that changes are the inputs that are streamed to that controller. Yes?
Can I ask you, just since this is such a rapid movement, I'm just curious, during that flip, is any state estimation occurring other than
Absolutely.
How
Yes.
is it able to figure out, based on its attitude?
First step is buy a good IMU. Yeah, no, spending a lot of time on estimation is a really key component. It's not really something I'm going to highlight in this talk, but it's absolutely fundamental. If you have a poor state estimate going into a controller like this, your predictions are going to suffer and the whole control system will suffer. Yes?
Maybe just related to that, can you point out what sensors you're using? You're obviously not just using an IMU.
So right here, the sensors are foot force sensors being used to detect and measure center pressure and ground reaction forces. There's an IMU in the pelvis, and then there's joint encoders everywhere. And that's it. That's for the state estimation. Yep. Yes?
So how close are these trajectories in sim versus?
This is the unsimulated trajectory. That is the trajectory being shown, and this is the robot executing it. So you can see they're pretty close, right? This is not a huge deviation. We'll get to that later, though. Yeah. So you can use trajectory optimization and then run those trajectories on the robot. Okay. You can also do sort of more artistic things, right? So things like jumping and jogging and flipping are things that are pretty conducive to trajectory optimization because we know how to describe those behaviors as costs and constraints pretty easily. I don't know how to write down costs and constraints for the mashed potato. Maybe that's just me. So for these types of behaviors, it's important to have a sort of more like a higher dimensional input that's maybe more stylized. And so there's a bunch of ways you can think about doing this. What we did for the dancing video was we took videos off of YouTube. We had an animator look at them, create an animation rig for Atlas, and then just render through his artistic eye those types of dances on Atlas. We took that purely kinematic trajectory now, fed it into exactly the same MPC controller, and that's how we produce the dancing. Now, it's not the case that you could just take this and have some naive tracking controller just run on the robot and magically it works. It's really the conjunction of these two things working together that makes this possible. So MPC is doing some useful innovation here to make this actually work out. Incidentally, since we've done this work, how the field of machine learning has moved on, it's pretty conceivable that you can imagine going directly from that video to that without a human in the loop, right? And so one way to think about what we've built here is that producing a sort of useful interface for models that could produce motion from video. It could be pretty cool. We haven't done that yet, but it seems feasible. Here's just another example. So Atlas appeared in a BTS music video, which is pretty cool. I had to be told who BTS was, but a lot of people knew, apparently. So again, we just found a BTS music video on YouTube, showed it to our animator. He created this, ran on the robot. Just to give a flavor for how long this took, I would call this one engineer day of effort to get this working on the robot. So this video, we did a first version of animation, ran it on the robot. It ended up being technically 2 days because our animator lives in Denmark and there was some time zone misalignment things or whatever. But the next day we did one refinement based on some stylistic observations we had from watching it run on the robot. And then that was it, and it was done. So we can do this kind of thing very quickly. Yes?
Can you speak to, how do you ensure that the animation is feasible in terms of?
We don't.
So it doesn't matter.
It's not feasible. It's like, yeah, it doesn't preserve conservation of momentum. If there's a flight phase, like, it's just not. It's not terrible. As you can see, you look at it, it doesn't look like it's on Jupiter or something like that, right? It looks kind of reasonable, but it's largely up to an artist's eye here, just to make it ballpark reasonable. Okay, you can also just directly do human motion capture, as you might expect. So here's just another couple of simple examples of my former student Patrick wearing a motion capture suit that has IMUs distributed throughout it and doing different behaviors. We take that, do a little bit of light cleanup to make sure feet don't penetrate through the floor and things like that, project it onto Atlas kinematics, run it through the MPC controller, and then we can do things like this. You might recognize a couple of these little emotes from our various videos, right? Atlas celebrations at the end. Now you know that was Patrick all along. These are all a bunch of one-off behaviors, right? In isolation, just tracking a trajectory. This is interesting, but marginally useful. And really, how you'd actually want to use this kind of a setup for doing more general mobility, maybe interacting with online planners, is something like this, where we build up a library of these trajectories. And importantly, we have to have some degree of extensibility, right, built in. We have to be able to not only select what is the closest behavior available in my trajectory library, but also make adaptations to that trajectory to fit the details of the robot's environment right now, right? So, for example, if I want the robot to jump onto a box, ideally I should only have to have a few jump on box trajectories in my library, and the controller should be able to adapt those within some range in order to jump onto any box that it shows up in the robot's environment. Likewise, because MPC is thinking about behavior over a horizon, this makes the problem of stitching together potentially inconsistent trajectories in a row a little bit easier. And so putting these things together with MPC is how we were able to do things like parkour. And so this video gives a kind of robot perception point of view for one of the videos that we produced of Atlas doing parkour. So what's going on here is the robot has a prior map of the environment and is doing plane detection and alignment of features to that prior map. Prior map is not perfect, but it's pretty close. And then we're able to annotate that map with desired behaviors in some cases, right? So in this case, we have pre-scripted paths that we want the robot to take. So these videos are not about showing the robots autonomously deciding how to do parkour. That would be a nightmare to try to film, right? It's just doing whatever it wants every time you run it. So really, these videos are more of a demonstration of our ability to quickly author a complex series of movements through interfaces and allow, a fixed control system and trajectory library in order to render the behavior that we're after. And so, for example, if we wanted to change something about this environment, switch around some boxes, add a different trick somewhere, whatever, that's a very easy thing for us to do as long as those changes are reasonably within the library that we have. So I think the library of all the behaviors that we had for doing a video like this is on the order of 100, 200 kind of size. And I don't know what percentage of those we actually were actually selected by the planner here, but it's a pretty sparse library. Yes?
I'm wondering for MPC for that task, are they only plan for the vision that it has to see? So I mean, you only plan to the point that it has to see, and also if you change the angle of view, you just replan. Is it a point?
Yeah, so the MPC is always planning a fixed time horizon in front of it. Usually the vision is able to see beyond the time horizon of MPC. That's usually the case. Yeah. Okay, so after all of that parkour work, we thought, well, how could we do better? And the obvious thing to do was to say, well, let's not cascade these optimizations anymore. Let's try to smash them together in one big MPC problem. And the hypothesis was that this should lead to better robustness, right? It should lead to better generalization. So the robot's able to coordinate now its dynamics and kinematics together. It should be able to do more impressive recoveries. It should be able to figure out more details of behavior based on environmental constraints. And we thought that it would probably also produce the ability to make behaviors without detailed trajectories as the inputs. So if we have the ability to solve for the entire robot body and dynamics together, we should be able to combine together references that don't fully specify every single joint and what it should be doing and have the controller figure that out for us. Of course, the downside to this is a much bigger and harder problem. So now we're solving an MPC problem that's nonlinear. It's got thousands of variables, tens of thousands of non-zeros, and we have to solve this very quickly online. There's a bunch of engineering effort required to make this actually work, and that's a lot of where our fantastic team of engineers spends their time in bringing this stuff to life. So what does this get you? Let me show you a couple examples. So let's go back to animation. Here's an animation. This isn't quite the animation. This is a log of the robot executing the behavior, but it shows you what the behavior is. So this is a sort of twisting, flipping thing. I don't know what to call it. We called it the sick trick because we didn't have a better name for it, but I think it's probably a proper name for it. If there's any gymnasts in the room, they probably know. So what is hard about this? As I said, we have an animator who's just kind of watching videos and making Atlas sort of do the behavior without any physics simulator other than his brain and eyes, right? And so the behavior that's being given to the robot is definitely not dynamically feasible. And that's really important. If I'm saying, I want you to track this kinematic trajectory and just figure out the dynamics as a separate thing, it doesn't work. We could not get this to work at all with the previous formulation. But if we put it in the new formulation, it does work. And why is that? Well, the controller now is able to do useful innovations like saying, okay, I need to push off really hard in order to get this kind of rotation. Maybe as I'm pushing off, half a second into the future, I'm going to be saturating my knee torque limit. And so I need to think about how I'm going to redistribute those torques so that I can still have that large ground reaction force in order to accumulate that angular momentum. And maybe once I'm in the air, I don't have the angular momentum I really wanted. So what do I have to do? I have to tuck my body in more in order to increase my rotational velocity to get my feet where they need to go. And if I'm going to tuck my body in more, I had better know that I can't intersect my limbs with one another in order to get some infeasibly small inertia, right? And so I can put the entire collision geometry of the robot inside of MPC and say, figure it out. Yeah, make yourself as small as possible. Yeah, rotate to where you go, but you can't penetrate yourself. And all of these details don't have to be figured out by a person designing a behavior, right? We can just provide an animation that's pretty close to what we want and trust MPC to work out the details. And so, yeah, that's the result you get. Here's just a bit of robot gore, just to give you a little behind the scenes of what it's like to create behaviors like this. So here, the robot completely snapped its leg in half and shoots oil everywhere. You can see the reaction in the back. This is part of the real joy of getting to work in the Atlas lab. It's like, you know, as a software engineer, you get to sit right here, and occasionally robots break themselves in half, and it's very exciting. It's amazing how quickly you become complacent with robots jumping around and flipping, though. Okay, let me show you some more stuff we could do. So this is basically the backflip I showed you earlier in the talk, where, again, we have optimized the trajectory to jump off of a 30-centimeter box, and then we ran it on the robot on a 30-centimeter box, and hey, presto, it works. Now, with a more descriptive MPC, I could take that exact same trajectory, run it on the robot, and say, hey, you have to jump on the flat ground right behind you, right? No other changes, and the robot's able to do that generalization completely on the fly. And what's it doing? Again, it's saying, oh shoot, I have to land on the flat ground. I don't have this additional flight time in my flight phase. I need to push harder. I need to spin faster, right? And I need to land in a different way. So I definitely get my feet where they need to go so that I can stand up after, but I'm willing to sacrifice these sort of configuration objectives in order to do it. Yes?
Are you still solving a QP but larger, or is it another?
Every single control tick is solving a single QP, and it is larger. Yeah, so it's a few thousand variables, kind of. Okay, you can take this one step further and say, well, what if I don't even have a trajectory, right? I want to start to create behaviors by just assembling other sort of like lower dimensional references and allow MPC to resolve all the joint configuration details. So here's an example of the robot walking, where the inputs are very naive. So it's a linear forward center of mass trajectory, a fixed configuration reference, just stand like a statue. So it's imagining itself kind of teleporting forward, and some advice about doing heel-toe walking. So left foot, right foot, left foot, right foot. And all the rest of the details come out of the controller. The arm swing is coming out of the controller, and you're getting out these sort of foot force profiles that just anecdotally line up with the kind of things that you see in the biomechanics literature. We just sort of notice this passively when reviewing robot logs. I'm not sure what exactly to conclude from it, other than, certainly this is not the thing you see when you're looking at like linear inverted pendulum-based gates on robots. And this is, I think, pretty compelling. It's not totally beautiful, right? Like if you were to go through and have an artist craft a walking gate, it would look better than this. If someone walked by you on the street like this, probably catch your attention. It doesn't look, it doesn't look amazing, but I would say, given what is provided to the MPC controller, this is very surprising to me. Okay, so where do we go from there? Well, as you might imagine, the next natural thing is to start to put Atlas to work, right? And when we thought about what does it mean for Atlas to do manipulation, what are the sort of key properties, key strategic advantages that Atlas might offer, some things came to mind, like its bimanual capabilities, its strength, its athleticism, its ability to move around the world quickly. And so we wanted to think about ways that we could do manipulation where the robot can move around objects that were sort of inertially significant, or it actually mattered that you had a coupled model of the robot and the thing it was manipulating in order to succeed. And we wanted to continue to build on this sort of generative approach that we're starting to see with the last version of MPC, where we didn't have to go through this whole process of trajectory optimization in order to create behaviors. We could start to more flexibly specify those behaviors with lower dimensional inputs on the fly. And we wanted to carry that into sort of object manipulation. And that was really the impetus for this last video that we released, and I'm sure many of you have already seen this before. And so the idea here was, obviously this is not how we imagine humanoid robots acting at job sites or anything like that. It was meant to be kind of a tongue-in-cheek connection to our prior work on parkour and what I think is a more serious and impactful objective of manipulation. But nevertheless, what we're able to do here is leverage exactly all of the behaviors that we used for parkour, unmodified, and simply layer on all of this manipulation objectives as part of the design process that was very fast and interactive. And then we were able to put this together in a routine that worked over and over and over again during filming. Yes?
So the foot sensors, does it also detect because the robot was walking on some plywood versus a solid ground?
Yes.
And stuff, so does it detect that and make adjustments to how much force it's applying, when it's hopping off of it or making the back foot?
It's treating the ground is the ground to it. It basically thinks about the ground as a rigid surface. And so But it's true that these surfaces are not the same. Like these blue mats are kind of thick gym mats, and so the robot's toes squishes into them when it toes off and jumps around. The plywood sort of rattles around. These wood boxes are slightly different, right? And so really what we've just done is made our controller and state estimator robust to all this variation without having to specifically classify what surface the robot's on. It's a good question. Yeah?
So I guess based on what you said, it seems like you have to specify the hybrid mode sequence, like
Yes.
which contact kind of happens in
Yes.
what sequence.
Yes.
You see that as a major bottleneck, and I guess going from that to optimizing the hybrid mode sequence seems challenging, but maybe it's doable with enough computation.
Yeah, so I think it is a limitation, right? And so the question is, where do you put that decision, right? You could say, well, the next elaboration of MPC is to make it contact implicit, right? That's one answer. Another answer is I have some upstream process that provides references inputs to MPC that's making that determination for me. I don't think we have the answer yet, but I do think that the online flexibility to change mode sequences is something we're excited about for sure. Cool. So this is a question that Ani sort of asked at dinner last night and inspired me to put this little behind the scenes slide. So the question was, what is the sort of process? Is there a big team of production people saying, how are we going to build the next YouTube video? And the truth is, all of these videos come from the creative minds of the people who create the technology, right? So here's a picture of the whiteboard where we were kind of figuring out what we wanted to do for this video 5 weeks before we filmed it. And what's kind of cool is we did it basically exactly that. And none of these, like picking up a tool bag, which we just called obj, we didn't even know what it was at the time. We knew we wanted to kind of run over a plank and do some kind of sick trick, whatever. We hadn't done any of these things at this point. We're just like, yeah, we could do that, right? And that's sort of fitting into this rapid authoring thing. So when we do these activities, it's not about, again, showing that you could build any kind of job site and just snap your fingers and the robot's going to do something equivalently cool. It's demonstrating our ability to quickly assemble a specific task using the tools and interfaces that we've been developing over the past couple of years. Okay. So let me tell you a little bit about MPC 3.0. And so the idea here is we're going to take our MPC 2.0, which has the whole robot kinematics and dynamics, and now we're just going to augment that with object models. Okay? So what that means is we're going to have rigid body representations of objects. So we're going to have the states of these objects, mass properties, and so on. We're going to have constraints that are defined between the objects that can come from desired and achieved grasps, for example. And then we're going to write basically force balance equations between the robot and the object. And then we can just put this all together. And now our MPC problem is getting even larger. But crank away again on the numerics, and you can do more and more. Here's just a visualization from a log of the robot during the video and showing the prediction of the board only. So, of course, the controller's predicting both the board and robot motion together. Here we're just visualizing what the robot's anticipating to do with the board. So what does this do for task specification? So this is where things got really cool for me. As soon as you start talking about manipulation, the idea of having a trajectory library that encompasses all the things you might want to do with the robot becomes a laughably bad idea, basically. And so you really need a way to have a control system flexibly combine components that are easier to specify and maybe specifiable by online planners, grasp models, whatever. And so as a simple example, when the robot throws a tool bag in this video, the way this was actually programmed was the following. We had a 180 jump trajectory that we had optimized like 2 years ago and used for various parkour things, just sitting in the code base. We said, okay, do that 180. Here's this object that's the tool bag, and we're just calling it like a cylinder that weighs approximately this much. That's really just a tool bag. It's filled with a bunch of random wrenches that we could find in the toolbox, and that's what's in there. We said, yeah, the object's roughly that. And I want you to throw the bag. So I'm going to give you this object trajectory that goes kind of from here up over here, and it enters a ballistic phase at some point over here. These are the inputs of the controller, right? These are obviously inconsistent, right? The robot's doing something totally different with his hands. You say you must be holding the bag for some period of time. So now the controller has to figure out how to accelerate the bag so that it hits the boundary condition at release to get the bag where we want it to go. It has to think about its combined inertia with the bag in order to change its angular momentum desired at liftoff so that it can actually get its feet all the way around. Yeah, and it has to couple all these things together. And we don't have to be bothered to like run an offline trajectory optimization that has a bag in it and has the robot and is throwing a bag. We can kind of just put these pieces together and ask MPC to solve it for us on the fly. Here's just another example of not only manipulating an object and trying to get it to do what you want to do, but actually using that object in order to achieve some other objective like balance. So this was inspired by tightrope walkers, which seemed like an interesting example of using object dynamics for some benefit. Here, it's a basketball being launched. It's really like an orange rigid sphere being whipped at the robot in simulation. And the robot's unable to stabilize itself without a pole. It does an admirable job kind of windmilling its arms around, but that's about it. And then by using reaction forces against the pole, it's able to sort of use that in order to keep its body upright and then eventually return the pole back to the balancing configuration. By the way, if you're interested in reading a little bit more about the underlying MPC technology for this, Robin Dietz and Tuan Kulin wrote a beautiful blog post on our website, and I encourage you to go check it out. It has examples like this embedded in it as well. So if we were to take that sort of pole balance analogy to the real world, we can ask Atlas to pick up something which may or may not be a Hyundai exhaust assembly, and just run the little parkour mini course that we have in the lab for when visitors come by. This is, again, these are just the trajectories that we made like 2 years ago, right? We didn't touch them. No more trajectory is happening here. All we're saying is, now please reach down and grab this thing. You're going to be holding this exhaust that has approximately this inertia, carry it over here and drop it. And it can leverage that same exact trajectory library and layer on these manipulation objectives all within MPC. Okay, so I think there's some good stuff here, in my biased opinion. I think what we've been able to do is create a very useful like abstraction layer that can be interfaced with either human designers, planners, other types of models, in order to realize interesting behavior on the robot. Of course, there are some limitations here. First of all, your prediction accuracy in MPC is directly related to its usefulness, right? And so this means that your models and your state estimate have to be pretty good in order for this to be useful. And if they're not pretty good, it can actively work against you. That's sort of one limitation. And this is maybe to Ani's point about like contact sequencing. There are still problems here that MPC really isn't solving. There's still some upstream problems that are difficult and worth our consideration. So the last few minutes, I'd like to just talk about another sort of thread of work. I'm going to switch robots on you and talk about Spot for a second. And we've been thinking about ways that you can use learned policies in conjunction with MPC in order to solve locomotion problems with Spot that would be challenging for us to solve through other design techniques or by implementing task-specific planners, things like that. So one problem that we looked at pretty early on was this problem of getting over irregular terrain with Spot. And so the idea here is, what if I could not just have a fixed reference or fixed reference library or some heuristic planner that I write that sequences things from a library? What if I could have a policy that runs at some rate, like 10 hertz, that's actively streaming inputs to MPC, right? So the idea is that I'm leveraging all the stuff that MPC is good at, right? Smooth locomotion that has good visual properties, that's stable, has some recovery capabilities and so on. But I'm delegating some of the hard part of using partial noisy visual observations in order to figure out where to put my feet and how to time it and how to encourage swing clearance and all that stuff. These are not problems that are impossible to solve using traditional engineering approaches, but these are problems that we think are amenable to techniques like reinforcement learning. And we've also found that when you have this kind of decomposition, the problem of taking a learned policy and putting it onto the robot can actually be pretty straightforward, right? So it's not that I'm learning the lowest level controller that's sending torques to or current commands to a motor where sim to real challenges can be exacerbated. Here we're living on top of a control stack that's already proven, and we're learning parts of the problem that are difficult for us to solve as engineers. Another example of this is, suppose I wanted to have Spot climb over sort of body-size obstacles in its environment. We certainly have the ability to do this through MPC and trajectory references. But it's, again, going to be the case that the ability to extrapolate any given trajectory to a variety of scenarios, different box heights, different initial conditions, is going to be limited. So we have to have a sort of larger library of behaviors and then some abilities to select from among those behaviors in order to generalize to a bunch of different scenarios. Whereas if, again, I can replace that trajectory library with a single policy that streams reference inputs to an MPC controller, then I can start to generalize to more initial conditions, more boxes, and so on. And likewise, because we're operating on top of MPC, putting things back onto the robot is actually not too bad. So here's just some examples of, you can take a single policy, present it into different scenarios, and then just run it and it's able to get on some pretty cool boxes. So what's good about this kind of approach? Well, I think it provides useful search bias to MPC, to reinforcement learning, right? So I'm not having to sort of vibrate around for hours and hours until I eventually find something that's a smooth and stable gait or bounding behavior. I already know how to do that, and I'm really focusing learning on the decision-making problem that is hard for me to solve. So that can be good. The downside is, even if you get a reduction in sample complexity due to that useful search bias, each individual sample for learning can be quite a bit more expensive to obtain. And that's because, at least in our case, these MPC controllers are pretty heavy computationally, and so each individual sample getting during RL can actually be quite a bit, so your wall clock time may actually increase. And then, of course, the last thing is that because you're using a model-based controller, in this case underneath the policy, you're going to be limited by the limitations of that controller. So if there are aspects of the problem that are unmodeled in MPC, then this can lead to catastrophic failures that may be insurmountable by whatever learning algorithm you apply. There are, of course, different ways you can use RL. You can put it in different positions in the block diagram here, and you can make different assumptions within MPC, and we've been exploring that kind of thing as well. So one just final example I'll point at is slip-resistant locomotion. So many customers of Spot have it operating environments which have variable friction and surprisingly huge changes from friction roughly 1.0 to like basically ice, you know, in half a second. And so the robot has to be able to quickly detect and adapt to those situations and ideally not fall down, and if it does, be able to get back up and keep going. And so here's just an example of what that sort of looks like. This is actually running Spot inside of the Atlas lab. The Atlas lab is an amazing playground for slip testing, right? Because this is a robot that sadly leaks oil on a quite regular basis. As I mentioned, they're quite old, and of course we explode legs occasionally. So all we really have to do is pull up our gym mats, and we have basically ice underneath them. We've measured the friction coefficient to be around 0.05 for Spot feet here. So very, very slippery. When you walk on it, you feel a little nervous and devote a lot of attention to it. So the way we set this problem up is now not to use our entire centroidal MPC stack. We're actually drawing the lines in the block diagram a slightly different way, so that we're not subject to having really good estimates that are fast and responsive for friction coefficients, things like that. We're instead giving a bit more control authority to the policy. So now we still know some things, so we can still embed some structure that, for example, we want the robot to trot around and then have a sort of relatively curated action space for RL that includes things like step frequency changes and step location changes and so on that we think are relatively complete for stabilizing locomotion. And then we can solve that problem and then transfer it to the robot. And this is the kind of stuff we were able to do with it. And I would say this is basically among the best examples of slip-resistant locomotion that we've ever produced at the company. And this is done, again, using a pretty, I would say, standard RL type setup and deploying directly from simulation to the robot. Yeah, this is, I guess, the obligatory Boston Dynamics robot abuse component of the talk. Hopefully I don't have any backlash due to this, but anyway. Okay, cool. So what's next? I think this is the most exciting time in the history of humanoid robotics, right? There's an incredible number of big players who are putting big investments behind this technology, and I think there's a sense that we're getting to a point where systems like this can do real jobs, right? And we're feeling really good about the technology we've been building over the last several years at Boston Dynamics, and that leveraging into new combinations with new types of learned models, planners, interfaces, that allow us to quickly adapt Atlas to perform a wide variety of tasks, many of which are real tasks that exist in real situations. And so here's just an example of some stuff we've been doing over the past few months, looking at combining vision along with data-driven grasping models, online planners for doing collision-free bimanual manipulation, along with all the MPC technology I talked about today, in order to move things around a sort of simulated factory work cell. Okay, I'll end there. Happy to take any questions. We are a growing company, I will say. We're hiring across the board, including positions on Atlas. So if this is something you're excited about, I'll be here all day. I'll be at the social. Happy to talk to you. And yeah, let me know if you have any questions. Thanks.
All right, we have some time for questions.
Yes.
Yeah, thanks, Scott. So for the learning part, you're using commotion. How do you imagine that apply to manipulation setting? Do you imagine still sort of learning for the high level and low level control deal with NPC, or are you more imagine like end-to-end?
Yeah, I think there's a bunch of different answers to that, and it kind of depends on what you're trying to do. So you could imagine learning like dexterous grasping feedback policies, right? That could be used in conjunction with MPC, where you basically just have like separation of domains of what parts of the robot are being controlled. There's a coordination problem there that I think is a little subtle that you have to figure out. But I think that's a great example of, you probably don't want to put the entire gripper and like some really gnarly like contact modeling and sensing and stuff like that into MPC. Maybe you do, I don't know. But that seems like the kind of thing that would be, based on what's going on in the literature over the past several years, something that would be very well amenable to RL. And it could be a place where you could use that to bootstrap a hard part of the problem while MPC kind of handles the part that we know how to handle. Yes?
So as you're trying to transition a lot of your robot platforms to doing work in like the real world and stuff like that,
Mm-hmm.
do you believe that platform like Atlas is versatile enough to engage in all those different industries, or do you still believe that it's probably best to design robots specifically for the industry, like kind of like how you have the, I forgot the name of the one in the middle,
Stretch. Yeah.
Kind of like how you have Stretch specifically for warehouse type settings and stuff like that. Do you think that it is best to go with like, okay, we need Stretch for warehouses, we need Atlas with this, we need this with that, or do you think that a platform like Atlas is versatile enough to just kind of go everywhere?
Yeah, I'm a believer in the sort of portfolio approach to robotics, right? So I think that it's a really smart move to build special purpose robots that solve tasks now, that can scale up and have an impact, drive revenue, and use that to funnel resources towards longer term plays, which I think are multi-purpose robots that can perform a wide variety of tasks on a single physical platform. And I think that's really the space where humanoids start to make sense. I think if you're ever talking about one specific task in a specific factory or whatever, a humanoid is going to be a questionable design choice, I would say. But I think they do offer a tremendous amount of flexibility. And so once we're able to cross that chasm of being able to rapidly program and adapt a robot, a single platform like that, to do a bunch of different jobs in situ, that's when they start to make a lot of sense and I think could be really impactful. Yes?
So I guess you mentioned that for some of these tasks, it's hard to manually specify task functions or reward functions. And I was curious about your thoughts on kind of reinforcement learning from human feedbacks. We have like human labelers, like saying this is good, this is bad, maybe for a variety of tasks.
Yep.
I guess it's popular sort of language models.
Yes.
Used a little bit with other kind of locomotion stuff.
Yeah, I'm tremendously excited about that avenue. I think it's anything we can do to get away from manual reward specification, I think is a positive move. And I think to whatever degree we can use direct human feedback particularly in applications like manipulation, I think is a really good move and certainly something we're interested in. Yep. Yes?
Yeah, when you train the IO policy with the MPC as a well controller, like you mentioned that the MPC part is quite computational and expensive.
Yes.
And is there any thought on how to improve that and get rid of the MPC? Because you're going to see more and more complicated tasks later. Yeah,
so one answer is, well, just distill MPC into a neural network and then just continue to improve from there from RL. Like that's certainly one answer that's plausible. There's probably still lots of room to make MPC itself as implemented as an optimization more efficient. Yeah, so I think there's plenty of things you could do to get around that. But in the architectures that we've been exploring where we want to run exactly the same MPC process in training as what we run on hardware, which we view as a sort of important design decision for a sim-to-real perspective, this has been an observation that we had. And also precludes using things like GPU-based training architectures, which primarily derive their benefit from being able to put the entire RL loop on a GPU. If part of your environment step is evaluating a CPU-bound process like a QP solver, then you start to lose some of the benefits you would get from that. So it sort of forces you into cloud training with lots of CPUs instead. So there are some pretty significant architectural implications of doing this too.
So the current QP solver is mostly on the CPU.
Yes.
Can you put it on the GPU?
No, we don't put it on a GPU. Yeah. Yes.
So I'm wondering if in the future you're looking into having a swarm of these robots communicate with one another and maybe work with one another, maybe in a warehouse settings or something like that?
Yes.
Or is it mostly just a single robot system?
No, absolutely. I think there's a long-term vision towards a lights out warehouse, right? Where you can imagine just a fleet of heterogeneous robots that are all doing different jobs in the warehouse. There's AMRs, there's mobile robots with arms manipulating packages. That's absolutely something we're interested in. And so fleet management is something that's certainly on our radar. Right now, we're mostly focused on solving individual robot tasks. So with Stretch, we just want to nail truck unloading, and then there's pretty natural follow-on activities that we'll try to release as products as well. But this is all building towards increasing automation throughout entire buildings, which implies coordination with robots. And there may be a long medium term too, where it's an environment that includes both people and robots. So there's lots of really interesting open questions around safety for systems like this and how you deploy these systems in order to work around people in a way that maximizes performance, but also meets safety regulations. Yes? Yep. Yeah. So there's, I think once you get to robotic assembly, then the floodgates are open, right? There's just an incredible number of jobs across all industries. But I think there's also a whole lot of jobs that are not detailed assembly, like assembly line type jobs, that are just moving things around warehouses. And those can range from boxes to totes to individual parts, and these individual parts can range wildly in terms of their appearance and geometric complexity, their weight, their size, right? And so there's a real wide space of just basically transporting type tasks that I think are very interesting and compelling as kind of a medium-term goal. And then from there, you can imagine that as being a sort of developmental stepping stone towards more challenging, I think, assembly type tasks. Yes?
So I'm just curious, you mentioned that when the animators come up with these motions for you to perform, they don't use any sort of physics-based engine, and the MPC deals with that. Have you ever given any thought to how it's performing in non-typical physical environments? Like, I'm particularly thinking about microgravity, for example. So if you could come up with something like that, you think the MPC is adaptable to performing in an environment like that, and you think Atlas might be capable of handling something like a parallel flight, for example?
Yes. I think that's one of the strengths of MPC is it would be a straightforward change to the model that change what gravity is. And pretty much everything would just work, I would imagine. Maybe I'm being overly confident, but I think I don't see any like major technical hurdles to making a change like that. Yeah, and we had many like early examples of we had Atlas in a Samuel Adams Super Bowl commercial where we like had it run across the lab carrying a giant keg on its head, and all we had to do is just like go into the model and attach keg to head, and then that's it. Like, and all of the normal jogging stuff just sort of worked. So there's sort of like, I think that's sort of in some ways an analogous change. It's just changing a different part of the physics model. Yeah.
If you were in a manufacturing setting, there are humans in the loop and it's operating near humans, is there, I guess the whole topic of safety, but maybe specifically with gentleness, you don't want to break someone's arm if you touch them accidentally?
Yes. I think that's an important problem. I'm not sure how relevant it'll be for robots operating in industrial settings. My guess is that for the near term, you'd probably want to have these robots spatially separated from people as much as possible. And that doesn't mean that they have to operate in like fixed infrastructure like cages and things like that with like traditional industrial robots. You can imagine like virtual fences and things like that being deployed as part of these robots, or having safety certified onboard sensing systems that can detect people and decelerate motion, and have backup safety systems that can guarantee that the robot will have a decelerated fall even if computers fail. Like, there's lots and lots of stuff I think you can do in order to make these robots safer to operate on people. But yeah, Atlas isn't super close to like hugging people right now, I would say. Yes.
Can you comment on applying MPC to conformable objects?
As long as you have a model for it, should be fine. It's a good question. We haven't really spent any time on deformable objects. There are people who are like building simulators that are pretty fast at simulating deformable objects. Some of these simulators are differentiable. So in principle, you should be able to apply optimization to these things. Even the ones that aren't differentiable, I think people are having a lot of success in recent years with Monte Carlo style optimizations being used as MPC. So I think there's plenty of opportunities to make progress on that problem if you wanted to focus on it, but it hasn't really been a focus of ours up to this point. Yeah.
What level of abstraction do you foresee for like people working with Boston Dynamic type robots? Because like if you look at like on the cars, for example, like they're mechanics, they're like they're orbiting people, right, that don't necessarily have like the computer science training or background and stuff like that. So if you are to deploy like a fleet or something and something goes on, I'm sure you guys don't want everything being sent back to you to like take over.
Absolutely. No, it's an excellent question. So I think our goal as a company is to deliver the most complete polished product as possible and have it be as accessible as possible. We can't assume that people have master's degrees or whatever in these facilities and they know how to write code for a Python API or whatever. It really has to be the case that these are usable and adaptable by the types of people who already work in these environments, and that is our long-term goal. And Stretch is a great example of this. If you look at the tablet interface for Stretch, there's some webinar stuff on the website if you want to see what that looks like. But it's a very simplified interface, and people are able to program the robot to do the tasks that it needs to do using an interface like this. And these are people who worked in the facilities originally, right? So I think that's a really important goal for us. We see a lot of the value proposition of these robots is not just as hardware platforms that end user experts can program to do what they want to do. We want to, as much as possible, provide flexible interfaces to customers so that they can make the robots do what they want to do without having to be robotics experts. Yes?
One last question. Go ahead.
I guess related to that question, is that interface a graphical programming language, or is that learning from imitation, that I could basically like paste the robot through what I want it to do and then have it do the task?
Yeah,
right?
maybe it's natural language, right?
It could be natural language.
Yeah.
Is there a preferred way of also kind of dealing with this, or what is?
Yep. So we tend to make use with both in Spot and Stretch tablet-style interfaces with touch screens and ability to drag things around and so on. I think in the short term, it's important to not only provide that type of interface, but also provide other sort of lower level types of interfaces. So you're not hamstrung by the current capabilities of whatever that highest level interface is. You try to make that as capable as possible, but also give people the option to go a little deeper to program the robot to do exactly what they want to do. And that's really the model for Spot is many different levels in which you can interact with the robot, and that allows it sort of to be a flexible platform for a bunch of different types of users. But I think our goal over time is to continue to make the interfaces that we expose to all people, all customers, as extensible and flexible as possible. But it's a moving target.
Yeah, maybe in the